Hello everyone, and welcome back to our series on quantum mechanics. In the last video, we wrapped up our discussion on the quantum harmonic oscillator by discussing the analytic method of computing its energy levels and eigenstates via asymptotic analysis. In this video, we will look at a new potential known as the Dirac potential and analyze its energy levels and eigenstates. As you might recall from previous lectures, the Dirac Delta is a generalized function or distribution, which can be thought of effectively as being zero everywhere except at a single point, where its value is basically infinite. We define the Dirac Delta based on the fact that integrating any function against it from negative infinity to positive infinity simply gives the value of the function at this point. This is known as the sifting property. In this video, we will consider a potential V of x equals minus alpha times delta of x, which is essentially a potential that is zero everywhere except for x equals 0, where it dips down sharply to negative infinity. Okay, so you might be wondering how we even find the bound states for this potential, as this potential is not even differentiable. Well, we can recognize that for x less than 0 and x greater than 0, this potential is 0. Consequently, if we can find solutions in these domains, we can attempt to glue these solutions together using the regularity boundary conditions of the wave function to find any bound states that exist. Since v of x is less than or equal to 0, we have that E must be less than 0 for any bound states, as if E is any larger, the particle would no longer be bounded by the potential. Since E is negative, solving the ODE yields exponential solutions rather than sine and cosine waves, as we got when E was positive, like in the infinite square well case. Consequently, for x greater than 0 and x less than 0, we have that bound states must have the following form. Since the wave function must vanish as x goes to plus or minus infinity, we can cancel the negative exponential term for x less than 0 and the positive exponential term for x greater than 0, leaving us with the following. Furthermore, since the bound state must be continuous at x equals 0, we have that the coefficients of both exponentials must be the same. Here, since the potential is infinite at x equals 0, we allow the bound states to not be differentiable at this point. Okay, so we have the following form of the bound states, but does this mean that we have a bound state for any choice of kappa? Well, not exactly. In particular, the delta function places a restriction on the size of the discontinuity in the derivative of the bound state at x equals 0. In particular, if we look at the TISE and integrate both sides from x equals minus epsilon to x equals plus epsilon, the integral of psi vanishes, and the integral of its second derivative turns into the size of the jump discontinuity in the derivative of psi at x equals 0. Algebraic manipulation then tells us that the size of the jump must be minus 2m alpha over h bar squared times psi of 0. Substituting in the form of the bound state, we can see that such a jump only occurs when kappa equals m alpha over h bar squared, meaning that this potential only has one bound state. We can find B by normalizing this state, of course, giving us the following eigenstate with corresponding energy eigenvalue E equals minus m alpha squared over 2h bar squared. Plotting the only eigenstate we have over the potential, we get the following. Okay, so this is clearly much different from what we observed with the infinite square well and the harmonic oscillator, as there we had countably infinitely many bound states, but here that is clearly not the case. Nevertheless, this is not the only difference to consider. For those wells, the potential went to plus infinity on both sides as x went to infinity. Consequently, it was impossible to have a state whose energy exceeds the potential energy everywhere. However, for this potential, notice that v equals 0 as x goes to plus or minus infinity. Therefore, if we have a particle with energy E greater than 0, we will have a so-called scattering state, which will not be normalizable. Let's see what such a state looks like in our case for a fixed energy. In particular, if we consider E greater than 0, we instead get complex exponential solutions to our ODE. By continuity, we must have that A plus B equals C plus D. Furthermore, using the same jump condition as before, we can perform some algebraic manipulation to find that C minus D has to be equal to A times 1 plus 2i beta minus B times 1 minus 2i beta, where beta is equal to m alpha over h bar squared k. Okay, so we have 4 different unknowns here, and seemingly no way to solve for them since we have no normalization conditions. It really seems like we're at a loss here. So, how do we make progress? Well, it helps to think about what actually is going on here. In particular, notice that if we attach the time evolution propagator to these complex exponentials, we get left and right moving plane waves. Suppose we only have an incident right moving wave approaching the barrier from the left. In this case, the wave will either get reflected, producing a left-moving wave on the left of the barrier, or transmitted, producing a right-moving wave on the right of the barrier. Notice that this interaction never produces any left-moving wave on the right side of the barrier. In these types of scattering experiments, we can typically eliminate one of the waves on one side of the delta function. In this case, we'd set d equal to 0. Using the continuity and jump conditions, we can solve for B and C in terms of A using algebraic manipulation. Now, imagine that A times e to the ikx is the incident wave. Since the probability of finding a particle is simply the absolute value of psi squared, we have that the probability that a particle is reflected, which we denote as the reflection coefficient r, is given as r equals the absolute value of b squared divided by the absolute value of a squared, which is equal to beta squared over 1 plus beta squared. Similarly, we define the transmission coefficient t, which is equal to the absolute value of c squared over the absolute value of a squared, which is then equal to 1 over 1 plus beta squared. As you would expect, since a particle can only either be reflected or transmitted, we have that r plus t equals 1. Substituting in the full expression for beta, we get the following expressions for r and t as functions of e. Consequently, as E increases, the probability of transmission increases, as you might expect. Of course, if we send a particle through, it cannot have a fixed energy as its wave function would not be normalizable. So we instead assume that the particle has a range of possible energies that are strongly peaked around a particular E. Something interesting to consider is what happens when we replace the delta well with a delta barrier. In other words, we change alpha to be minus alpha. While we now get rid of the bound state, we actually have the same exact expressions for r and t. This is fascinating since it means that even though v equals plus infinity at x equals 0, a particle with finite energy can still pass through the barrier with non-zero probability, which would never occur classically. This process is known as tunneling. I should also mention that even if v was a finite positive number at x equals 0, for e greater than this new v, there would still be a non-zero probability that the particle would be reflected, which also does not happen classically. For the last topic of this video, I want to talk about a somewhat special topic, the double Dirac potential. Let's see how to go about finding the eigenstates and energies for this new potential. Where do we even begin? Well, recalling our initial discussion on the single Dirac potential, we simply solved the TISC for each domain separated by the Dirac and then combined the resulting solutions. This case is no different, giving us the following ansatz of a solution. Using the same asymptotic conditions as before, we can eliminate these terms. Okay, but now we have 4 different unknowns, so what do? Well, in these types of situations, it's usually beneficial to go back to basics. Recall our discussions on symmetry. Since the potential is even, we must have that any eigenstates for a potential are either even or odd. Consider the even solutions. This requirement forces us to choose the coefficients as follows. By continuity at A, we have the following relation between B and C. Using the same jump discontinuity condition as before, but now at x equals a, we can perform some algebraic manipulation to get the following transcendental equation for kappa. Note that we can also arrive at the same equation by simply looking at the other jump discontinuity at x equals minus a. We of course cannot solve this analytically, but practically speaking, we can solve this either graphically or using numerical techniques. Here's what a typical graph of these two functions looks like. As you can see, regardless of the slope of the line, which is the only thing that changes if we use different values of alpha and of the other parameters, there is always one intersection point, which we will denote as kappa equals kappa naught. Consequently, we have that there is a single even energy eigenstate with energy given by minus h bar squared times kappa naught squared divided by 2m, where the form of the eigenstate is given as follows. Of course, you can compute C by normalizing the eigenstate, but I'll leave that as an exercise for the viewer. For the odd case, we instead have the following structure to our solution. Repeating all the same steps as before, we instead get the following transcendental equation. Plotting this, you can see that we instead have this line with a negative slope that starts at the same place as the exponential when kappa equals 0 and then decreases. Consequently, you can see that if the slope is at least as steep as the tangent line at this point, there will be no intersection with kappa greater than 0. Consequently, comparing the derivatives at kappa equal to 0 of both sides of the transcendental equation, we can see that we only have an odd eigenstate if and only if alpha is greater than h bar squared over 2ma. If this eigenstate exists, it will have the following form and energy, where kappa equals kappa 1 again represents the intersection of the two curves previously shown. Based on the number of nodes, it should intuitively be clear that the even eigenstate, which is always non-zero, must be the ground state, while the odd eigenstate, which is only 0 at the origin, must be the first excited state. Altogether, we examined the Dirac potential as a useful tool for studying the behavior of a particle near a sharply dipped well in both bound and scattering contexts. In the next video, we will discuss the finite square potential well, making good on our introduction to scattering. I hope you enjoyed this video, and I will see you next time.